Day 46, page 975, problem 59. This one's a little bit more involved. First of all, they give us a lot of information, but we're looking at two patterns on top of each other. We're shining two different colors of light, while really shining the pattern from one element, from a sodium lamp, I should say, from one object. And we're seeing the constituent colors of light that are in that particular light source. And here we have two yellow fringes that you'll be seeing on the screen that will repeat, but in their first order, they'll have an X value. I'm calling it XA and XB for the two different colors of yellow. XA, X sub A, will be a little bit further out because it's a bigger wavelength. It'll have a slightly bigger distance from the central maximum. So I'm computing the first order for each of these in the upper diagram, or the upper right-hand calculations up there. And you'll have to figure this out to like 7 sig figs, and then subtract. Take the bigger value, X sub A minus X sub B. But before you even do that, you got to figure out how far apart the fringes are, or that should be the slits. Down here in the lower left, okay, I did that because if you have 10,000 lines per centimeter, you end up with about, with 1 times 10 negative 6 meters per line. You reciprocate 1 over 10,000 is 1 times 10 negative 4 centimeters per line, and then divide by 100 to get into meters. So that's how far apart these slits are. So then you went up to the upper right here, and I plugged in carefully, well, once again, 7 sig figs, you can do all that, the two different wavelengths, and you'll get two different distances from the central maximum. You subtract those, that'll tell you how far apart those two yellow lines are, kind of like when we were looking through those black spectral tubes to evaluate or analyze the emission spectrums from the different gas sources last year for helium and hydrogen and neon. So you see those particular patterns for each of the different elements. Anyways, do that math there. But now I'm going to go to part B. They want you, in part B, you can pause and actually calculate that. In part B, they want you to use the non-approximation, because that what we just did up there was valid for small angles, and even at small angles it's still approximation. When you go to 7 sig figs, you're going to get some slight issues. But now we want to use the d sine theta equals m lambda. We're going to do this twice. Let me pause for a second. Okay, so in part B now we're using the more precise equation, this equation here, d sine theta equals m lambda, and we're going to apply that to both of the different wavelengths. So I've solved for sine of theta. So you have this equation, which is the same equation, just to move the d over, and I'm going to find the angle to these two particular spectral lines, A being the theta, the angle theta sub A is the angle to the yellow line that's got a wavelength of 589.5923 nanometers. Well, once again, I forgot to put in there nano, so make sure you put in times 10 negative 9th when you do the computation. That's same is true in part A. So you figure out theta A and theta B to these two spectral lines. Now once you have those angles, now you can go, if you look back at the diagram here, and let me highlight this while in the diagram. So you have this triangle right here, where this bottom leg is L, and then the X is on that short leg, and we have the hypotenuse, which we really don't care about, but the bottom line is, if you take now the tangent of those angles, of that angle, that thin, long angle, but the tangent of the angle, which we know theta A and theta B to each of the two spectral lines, the tangent of the angle is X over L. Or in other words, X equals L tangent theta. So going back down over here to the bottom right again, using the thetas that we have, bottom right, that we just calculated, we're going to get X sub A, how far X is from the central maximum, by taking L, which is 1 meter, times the tangent of the angle, and make sure you're using about 7 sig figs, tangent of theta A. That'll tell you how far it is to that first fringe line. And then same thing for XB. The distance of that one will be 1 meter, that's L, the distance to the screen, times the tangent of theta B. Once you have that figured out, you can take, like we did before, x sub A minus x sub B to figure out how far apart those two fringe lines are, and it should be 1.13 millimeters, or in other words, 1.13 times 10 to the negative third meters. Good luck with that. Make sure you carry on like 7 sig figs throughout, and don't forget the nanometers for those wavelengths.